In this video, we will explore a heap program that uses two-dimensional blocks for matrix multiplication. Before we dive into the heap code for matrix multiplication, let's first review how matrix multiplication is typically computed. Suppose we have two matrices A and B. Matrix A has n rows and m columns, and matrix B has m rows and w columns. After multiplying the matrices A and B, the resulting matrix will have the number of rows equal to the number of rows in matrix A and the number of columns equal to the number of columns in matrix B. In this particular case, the resulting matrix C will have n rows and w columns. To compute the product of matrices A and B, we first take the dot product of the first row of matrix A with the first column of matrix B. This gives us the first element in the resulting matrix. We repeat this process for all rows and columns in A and B to obtain the complete resulting matrix. Let's now take a look at a CPU implementation of matrix multiplication to gain a better understanding of the process. This code is a program that multiplies two square matrices using CPU. It has a function called CPU matrix multiplication that takes in three pointers to integer variables as well as an integer value. The pointers A and B represent the two matrices to be multiplied, while the pointer result points to the matrix that will contain the multiplication result. And the integer n specifies the size of the matrices. The CPU matrix multiplication function uses nested for loops to multiply the two input matrices. The outer two loops iterate over the rows and columns of the resulting matrix, while the innermost loop calculates each element of the result. The multiplication is done by iterating over the row of matrix A and the column of matrix B, multiplying corresponding elements and adding the result to a temporary variable. Once the innermost loop is completed, the temporary variable is stored in the corresponding element of the resulting matrix. The main function initializes two matrices A and B with random values using the random function. Then the CPU matrix multiplication function is called to perform the matrix multiplication and store the result in the C matrix. In this section, we will look at the implementation of square matrix multiplication using heap. The first thing to note is the inclusion of the header that is necessary to use the heap runtime calls. We also added macros for the size of the matrices and the number of blocks per grid, which is set to 16 and 256 respectively. Now we will take a closer look at the heap kernel. The purpose of the kernel is to perform the square matrix multiplication, and it takes in four parameters, pointers to the matrices A, B, and C, along with the size of the matrices n. Inside the kernel, the first thing we see is the thread indexing. Since this is a two-dimensional matrix multiplication, thread indexing is done separately for row and column. These two lines of code will assign index to the thread in the x direction and y direction so that they can match up with entries in output matrix. Each thread in one specific block is identified by threadindex.x and threadindex.y, and each block in a grid is identified by blockindex.x and blockindex.y. After the thread indexing, we initialize the variable sum for adding all the elements in the selected row and column. Then we check the row and column does not exceed the number of actual rows and columns in the matrices using an if statement. We do this to prevent unnecessary threads from performing operations on the matrices. A single for loop inside this kernel means each thread is doing a dot product of the elements of the row in matrix A and the corresponding elements of the column of the matrix B. After the summation, the result is stored in the corresponding cell of matrix C. We have also included the CPU matrix multiplication function for the verification of the implementation in the later slides. In this function, there are four parameters including the pointers of three matrices, namely h_a, h_b, h_result, and size of the matrices n. This CPU code computes the sum and then store it in the corresponding h_result matrix. Let's look at the CPU code. To start, we declare pointer variables with integer data type. Next, we allocate the host memory for the matrices h_a, h underscore b, h underscore c, and h underscore cc. Here h underscore cc is used to store the CPU result so that we can verify the accuracy of our calculation. In this block, we are going to randomly generate matrix A and matrix B on the host. In these loops, we fill the matrices with random numbers. Next, we declare the GPU memory pointer variables having integer data type, and we use heap malloc with 2 arguments to allocate the memory on the device. The 2 arguments are the pointers and the size of memory to allocate. Here we declare 3 pointer variables d underscore a, d underscore b, and d underscore c, and allocate data on the GPU for these 3 pointer variables. The next thing we do is copy the data from the input matrices h underscore a and h underscore b from the CPU to the GPU. The heap memcopy API call takes 4 arguments: the destination matrix d underscore a, followed by the source matrix h underscore a, and the size of the matrices and direction of the transfer, which is heap memcopy host to device. Then we launch the kernel, but before launching the kernel, we need to define the number of threads per block and blocks per grid. The data type for the dimension of grid and block is dim3. In this example, the grid is just a block size by block size grid, where the value of block size is set to 16 in the very beginning of the code. And so the number of blocks, n blocks, has to be n divided by block size, as n is the size of the matrices. We use the ceil instruction here to get the next integer number. Therefore, the number of blocks in a grid is n blocks by n blocks. In this way, we can use more threads than necessary and prevent them from working on the matrices within the if statement that we wrote in the kernel. Finally, heap device synchronize function is used to wait until the kernel execution on the device is completed before processing with the CPU code execution. This ensures that the CPU does not access any data that is still being processed by the GPU. After the kernel execution, we can copy the result from the resulting device matrix d underscore c on the GPU back to the CPU using the heap memcopy, same as before, but this time the direction indicates heap memcopy device to host. After moving data back to the CPU, we verify the results. Next, we also call the CPU function so that we can verify the results later. The CPU function includes 4 arguments, including the input matrices h underscore a, h underscore b, followed by the resulting matrix h underscore cc and the size of the matrices respectively. During the verification, we check if the value of the data in resulting matrix calculated in the CPU matches with the resulting matrix calculated using GPU kernel. If the resulting matrices match, then we print matrix multiplication is correct, otherwise we print the error at index. Then we free the memory we allocated on the CPU and GPU memory and return 0 to indicate the program has run successfully. In the next video, we will provide a recap of this unit and summarize the key concepts we have covered so far. We will also provide an assignment to give you the opportunity to practice what you have learned and solidify your understanding of heap programming.